All right, we're about to enter the high-NA lab.
Behind this highly secured door in an ASML cleanroom, there's a giant $400 million machine.
It's bigger than a double-decker bus.
Made with such closely protected technical specificity.
Very complex, the most advanced machine tool in history.
That no filming's ever been allowed, even by ASML's own team, until we flew across the world to see it.
We're here at ASML's headquarters in the Netherlands, where 100% of the world's extreme ultraviolet lithography machines are made, and now the next generation machines called high-NA. We had to wear these bunny suits to protect these extremely precise machines from getting contaminated by our own hair and skin cells.
This is high numerical aperture, high-NA, the new generation of EUV machines, the only machines in the world capable of printing nanoscopic blueprints onto the most advanced chips. NVIDIA, Apple, Taiwan Semiconductor, Samsung, Intel, none of their advanced chips can be made without EUV.
And this company has that market completely cornered.
The first high-NA machine was installed in the US at Intel's Oregon Chip Fabrication Plant, or Fab, last year. Only 5 have ever been shipped.
Indeed, the machine is so big you can't ship them in once, so we break them into parts.
Now they're being ramped up to make millions of chips on the factory floors of the few companies that can afford them: Intel, TSMC, and Samsung. ASML says eventually high-NA will be used by all its EUV customers, other advanced chip makers like Micron, SK Hynix, and Rapidus.
Without EUV, without very advanced logic manufacturing, most probably AI cannot happen.
CNBC went from ASML's labs in California all the way to its Veldhoven, Netherlands headquarters to bring you this never-before-seen look at the world's most advanced chip-making machine, and to ask its makers exactly how it works and what could go wrong amidst Trump's tariffs, export controls, and a new training facility coming to the U.S.
I would say it's been a very risky investment because when we started, well, there was no guarantee the technology would work.
By 2018, ASML had shown that EUV was possible. And it's the same process used in high-NA. Here's how it works. Chips are built in a grid formation on thinly sliced wafers of silicon, each with up to 100 thin layers that make up billions of transistors that determine what the chips can do. These layers are printed using lithography, extremely precise rays of light projected through a mask of the chip design until they hit the surface of the wafer that's been coated with photoresist chemicals. ASML's older generation DUV machines, which it still makes, use rays of deep ultraviolet light with a wavelength of 193 nanometers. Nikon and Canon in Japan are still competitors in DUV. But ASML's real breakthrough came with that bold bet on a technology many thought was impossible, using even shorter wavelength extreme ultraviolet light, EUV, something that to this day no other company does.
A few more people tried for many years, but the size of the investment, the commitment you have to have, I think discouraged quite a few people.
Transistors have gotten so small, down to 10,000 times thinner than a human hair, that ASML decided to create its own source of smaller, more precise EUV light. At a wavelength of 13.5 nanometers, it's the width of just 5 DNA strands laid side by side.
So small that it gets absorbed by almost everything, and that's why this whole system needs to be in a vacuum.
This tiny thread may look like the strand of a spiderweb, but it's actually molten tin being shot out at 50,000 droplets a second. The tin droplets are vaporized with a laser, and those tiny explosions are what emit photons of EUV light.
This is called a CO2 laser. It's been used in the car industry for many years. They would cut through steel with one of these. We use 4 of them to shoot at one of these tiny tin droplets to generate a plasma which is hotter than the sun. That plasma generates EUV, and that EUV is captured by this collector mirror that comes from calcite. That plasma generates EUV, and that EUV is captured by this collector mirror that comes from calcite and brings the light into our scanner.
The light bounces off of mirrors that aim it through the lens, much like how a camera works. But because EUV gets absorbed by typical mirrors, German optics company Zeiss made specific mirrors just for ASML that are the flattest man-made surfaces in the world.
And then the light is emitted through the projection optics onto the wafer, which is about here. So this is the wafer table.
When the EUV finally hits photoresist chemicals on the surface of the silicon wafer, it prints the minuscule blueprint that makes up the chip. The aim needs to be so precise, TSMC says it's equivalent to shining a laser from the moon to hit a coin on the Earth. EUV made up less than 8% of ASML's total number of machines sold in 2024. 44 EUV machines versus 374 cheaper DUV machines. But with a price tag of $220 million, EUV made up 38% of ASML's system sales revenue.
But the cost of the chips, the tools of the chips, the tool is going to create is going down.
Because you're the only company in the world that makes these machines, what's stopping you from setting the price even higher?
Well, what stops us is Moore's law says that we need to continue to drive costs down. This allows you to go to the next node, and then the next node, and then again the next node. If this was to stop, then everyone gets stuck.
ASML began developing its latest $400 million high-NA machines around 2016. Inside, all the same processes still happen with the same EUV light source, but there's one key difference.
We increase the aperture of the opening angle of the lens.
High-NA stands for high numerical aperture, meaning it has a larger lens opening, increasing the angle at which the light is captured by the mirrors. More light coming in from steeper angles allows high-NA machines to capture increasingly small designs on chip masks, so they can be projected in one exposure step, whereas original lower NA machines reach higher resolution to project these tiny designs using multiple exposures through multiple masks.
1 become 2, then 2 become 3, 3 become 4. And when the number increases, it gets very complex process-wise, and the yield goes down.
But with a higher NA, resolution improves, and the small designs can be printed with fewer masks, saving time and money.
The larger the number, the smaller the thing you can print.
But this higher NA also comes with a much higher price tag for one main reason.
The higher the NA of an optic, the bigger the mirror you have to use, and therefore the bigger the system.
These machines also take up a huge amount of power.
How much power do these machines take?
I think they take too much. If we don't improve the power efficiency of our AI chips over time, the training of the models could consume the entire worldwide energy. And that could happen around 2035. Since the moment we started EUV, 2018, we have reduced the power, the energy needed per wafer exposure by more than 60%.
ASML says its machines print about 200 wafers per hour, 24/7, 365. The goal is several hundred per hour.
You can print, at the end of the day, millions of these wafers per year.
At a conference in February, Intel said it started making chips with high-NA, using it for some 30,000 wafers so far, and that it's about twice as reliable as previous models. And Samsung said high-NA could reduce its cycle time by 60%.
High-NA means two things. First and foremost, shrink, so there's more devices on a single wafer. And secondly, by avoiding multiple patterning, you can make them faster and you can make them with higher yield.
In reality, every chip is made using multiple different lithography techniques at different resolutions.
Every chip consists out of like 100 different layers. Most of the layers are actually made with deep UV, which is a much smaller system.
Legacy DUV machines sell for less, $5 million to $90 million, but still make up over half of ASML's sales.
The older machines are in high demand. Many of the chips we use in our daily life do not require EUV. If you press the button to open the window in your car, unlikely an EUV-based chip is needed.
Turns out ASML sells a lot of its legacy machines to China, although US export controls prevent it from selling EUV there. It's a ban that started under the first Trump administration.
The Trump administration is very focused on ensuring that China does not get access to the most advanced tools and chips that are required to power AI.
So without access to ASML's EUV machines, could China develop its own?
I feel like it's a real long shot that China could enter this space. But right now, China's really figuring out ways to take things like 7 nanometer